So excited to take y'all into transition state theory. One of my favorite theories, in particular, Henry Eyring, brilliant physical chemist. And there's a really great little biography, very short biography of Eyring in the Laidler handout. Okay, so again, I am this lecture corresponds to Laidler, the handout, physical chemistry Laidler textbook. In particular 9.9, but I've included 9.6 to 9.8 also just to give you the breadth. Atkins uses a slightly different notation. Atkins also assumes that you have seen statistical mechanics, which means he's going to develop Eyring's equation from the partition function. We don't have those skills, so we're going to take Laidler's approach, but Laidler's more of an expert because he worked with Eyring and actually wrote transition state theory with Eyring. So Laidler knows what he's talking about. Okay, so this picture. So hopefully by now we're all comfortable with this idea that you have reactants to products along a reaction coordinate. This is different than extent of reaction. Next week, you're going to dive into potential energy surfaces in which reaction coordinate has meaning. And that's where this comes from. So this is where you'll focus on the potential energy surfaces. So this is different than progress of a reaction, which is related to how N is changing. This is just a reaction coordinate, which is an energy idea. Okay, this is more energy, and you'll see what I mean talking about next week, but keep that in mind. Reaction coordinate, different than extent of reaction. Okay, so there's a certain energy, but this is still potential energy. So there's an energy associated with the reactants, there's an energy associated with the products, and this value right here is your delta G of reaction. So if it's negative, that means that the reaction is spontaneous when you compare reactants to products. So this is a spontaneous reaction, but you might be saying, but Allison, there is a transition state right here. It's not spontaneous because you have to put energy into the system in order for the thing to go forward. That is true. That's where we talk about this, what's called the transition state. So I'm going to write this as A plus B is in equilibrium with P, where here we have K1 and then a K minus 1 rate constant associated with the forward and then the reverse reaction, respectively. So if I want to say that the equilibrium constant Kc of this, again, equilibrium is defined when the rate of the forward is equal to the rate of the reverse. Not that the rate constants are equal, but the rate of the forward is equal to the rate of the reverse, which means the ratio of K1 to K minus 1 is the equilibrium constant for that setup. Okay, so let's relate this then to the Gibbs potential. So at standard conditions, we know that the standard Gibbs energy is equal to minus RT log of K. And this comes from delta G is equal to delta G standard plus RT log Q, where this is our reaction quotient, which is dependent on where you are in the extent of reaction, which is different than the reaction coordinate. Okay, but at equilibrium, this goes to 0. And then we can determine what our standard condition is. And then as you realize or remember from the exam, this T can only be 298 or 25 Celsius, 20 Celsius, 0 Celsius, specific to what delta G standard was determined. So this is a very limited function. You'd have to use Van Hoff's equation if you wanted to find T or delta G at some other T, which means you'd have to take into account the enthalpy of vaporization. But I digress. Okay, where was I going? Right, so let's use this to explore Kc. So log of the equilibrium constant is equal to delta G over RT with a negative sign, which is equal to log K1 over K minus 1. Cool. So I've just included in the equilibrium constant in terms of its forward and reverse rate constants. So the power of logarithms, I can say log K1 minus log K minus 1 is equal to minus delta G, oops, sorry, these should be standard, over RT. Groovy? Well, I can also then break this up into two different delta G. So this is where Eyring's brilliant in a lot of places, but approaching this as two separate delta Gs to where you have, and I'll use red, why not? Delta G1, this is delta G1, And then we've got, let's go with purple. This one, delta G minus 1. Cool? Okay. So this is then equal to minus delta G 1, and I'm going to put this little double dagger insignia, RT minus, whoops, it's going to be plus delta G minus 1 double dagger over RT. Okay, so it really should be minus because, and actually I'll just include that so it's very clear, minus a minus delta G. So this becomes log K1, and this becomes log K minus 1. Is everyone cool with this idea? And since each of these are a designation of the reactants to the transition state or the products to the transition state, we're going to put a label here as a double dagger. Double dagger meaning transition state, which is different than the activated complex. The activated complex, which happens to be in energy at the transition state, is the form of the whatever molecule thing that's coming together. But the transition state is the energy associated with the activated complex. Okay. So we've got now log K1 minus log K minus 1 is equal to these two guys, or gals, depending. And so now so hopefully you can see the connection between these, where this represents log K1, this is the forward reaction, and then here the standard Gibbs associated with the transition is from the reverse reaction, which would be going P to A plus B, which is P to get to here. Okay. And if you think about how is that related to the rate constant, well, the rate constant dictates the speed. It's that quantity factor of you have a rate is equal to some K times the concentration of your product, or sorry, concentration of your reactants. If this value scales is really big, that means you're going to have a high rate. If this value is really low, you're going to have a low rate. So the K values can tell you the, I don't want to say the agility, but the capability of getting to that transition state either from the product side or from the reactant side. Okay. Now I'm going to introduce another factor. Actually, it's a term into this relationship. So I've got log K1 is equal to log nu 1, actually just nu, minus delta G double dagger over RT, and this is delta G double dagger 1. And then I got log K minus 1 is equal to log nu minus delta G minus 1 double dagger over RT. Okay, so what is this nu? And I should say Atkins uses kappa, which is like the fancy K. There are too many Ks in the world, which is why Laidler says we're going to use nu. But what nu represents is what's called a transmission coefficient. Okay, log nu equals the transmission coefficient. Okay. And what you can think about the transmission coefficient as a so many things. It's almost as if it's a probability of a reaction occur, or the ability for the reaction to occur. So you've got you can assume that it's 1, so it's almost like a percentage. So a transmission coefficient of 1 would mean that log 1 is 0. So that means that the log K of the reaction of the rate constant. So the log of the rate constant is equal to minus delta G double dagger of the reverse reaction. So this delta G is equal to log K value divided, or log K minus 1 divided by RT. If this is not 1, that means that this is some sort of quantity. You're going to have a slight difference between the maximum value you can get of this. Okay. So there's going to be a less likelihood of the transmission or the outcome of that process. Cool? Pause, rewatch to sort it out. Okay. So if I then solve for, so I'm going to focus on this one. So if I then solve for K1, so K1, that's then going to equal nu e to the minus delta G double dagger over RT. Take a minute and think of how I got that. Go team. Okay. So now we are in the exponential. This is starting to look familiar. Do I see an Arrhenius coming up? Yes, you do, hopefully. Okay. Well, you know that delta G, thank you Gibbs, is equal to delta H minus T delta S. And so we are comfortable with this idea of using the Gibbs relation between enthalpy and the entropy quantity T of entropy. And don't forget, this is an embodiment of the second law, which says that there is no process that is spontaneous, which results from the complete conversion of heat into work. You're gonna lose a little bit. The same is true to get to the activated complex, that structure, or to reach the transition state in terms of energy. There is no result or no spontaneous result in which you can put all of the heat energy into work energy to get to here. You're going to lose a little bit. And that's the activated energy, or sorry, the energy of the activation state, or the activation energy, this delta G double dagger. So if we put this as the enthalpy of activation and now the entropy of activation, we can include this into this delta G, and that gives us nu e to the minus delta H double dagger minus T delta S double dagger over RT, which we can then break up into transmission coefficient e to the minus delta H double dagger over RT, e to the delta S double dagger over R. Notice how I've now got a positive in front of this value here, and I've got T missing. So the T's canceled, and then this negative here became a positive. So I can rewrite this K1 equals nu, transmission coefficient, e to the delta S double dagger over R, e to the minus delta H double dagger over RT. Groovy. Okay,